In this video, we're going to apply the law of thermodynamics and conservation of energy to determine the final temperature of a mixture of two liquids. So the situation is this. I'm going to have one container here of water, and that water is going to be 500 grams, mass of 500 grams. The specific heat of water, as we've seen before, is 4.18 joules per gram Celsius. In the past, you've seen 4,180, but that was per kilogram Celsius. So this is per grams. So there's a factor of 1,000 difference. So it's 4.18 joules per gram Celsius. And it's at initial temperature of 100 degrees Celsius. We're going to mix it with a second liquid that has a mass of 500 grams. And the specific heat of that liquid is going to be 10 joules per gram Celsius, and it's going to have an initial temperature of 10 degrees. And what we want to find is the final temperature if I mix those two things together into one mixture. So the basic idea is that we have some thermal energy stored in the water, we have some thermal energy stored in the second liquid, which we don't know, but we do know the specific heat of. One's at 100 degrees Celsius, one's at 10, and we want to find the final temperature. So this is a conservation of energy problem. So initially we have, or the first statement we want to say is that the energy initial, or thermal energy, heat energy, in each of the two independent liquids is equal to the final temperature, final being the final thermal energy of the mixture. So what we have is this. We have, just to visualize, the heat energy in the first bucket, the water, plus the heat energy in the second bucket is going to equal the heat energy in the mixture. Again, this is assuming 100% efficient, we don't lose any energy, but that's the basic idea. So from that, this is water. This is the second solution, which may be like and this is the mixture here. So the energy equation for this becomes, finish the equal sign there, it's M of the water, C of the water, temperature of the water, this is initially, which represents the energy in this bucket here, plus the mass of the solution, the specific heat of the solution, plus the temperature of the solution, equals the mass of the water, specific heat of the water, times the final temperature, I'll call it TF for final, plus mass of the solution, specific heat of the solution, temperature final. We have a common temperature. So a little mathematical thing we do here is that we see that T final is common to both, so we're going to factor that out. Because when the water and the solution settle, they settle at one common temperature. So I'm just going to factor that out like you would in algebra class. There. So this is the thermal energy of the water initially, the thermal energy of the solution, and then here you can see after I factor out the final temperature, this is the final thermal energy of the mixture. Given all of these values, which we know, the mass of the water, specific heat, temperature of the water, mass of the solution, specific heat of the solution, and temperature of the solution, the only unknown we have here is the final temperature, and that's what we want to solve for. So the final temperature is basically this initial energy divided by that mass water, C water, mass solution, C solution. So this equals mass of the water, C of the water, temperature of the water, this is initially, plus mass of the solution, C solution, temperature solution, divided by what's in parentheses right there, mass of the water, specific heat of water, plus mass of the solution, specific heat of the solution. So step 4 is basically mathematics. Getting to this equation is the physics of the problem. So if I plug in the numbers here, I get 500 times 4.18 times 100 plus the mass of the solution is also 500 grams times its specific heat is 10, and it's initially at 10 degrees Celsius, given those values there, and we're going to divide by 500, the mass of the water, times the specific heat of the water, 4.18, plus the mass of the solution times the specific heat of the solution. So there's a one-to-one correspondence between each of these terms here, and if you do the math here, you get a final answer of 36.5 degrees Celsius. So it looks like there's a big temperature change. We go from 100 down to 30. And if you look at the specific heats, it looks like the specific heat of the solution, 10, is more than double that of water. It's a good heat absorber. It absorbs the energy, thermal energy, very efficiently. So if you want to use the word efficiently. And so we come to a temperature of 36.5 degrees Celsius. So this is an example how we can determine final temperatures of a mixed solution. And once we have this basic equation, we could redo the problem with any mass, any specific heat, any initial temperature, any specific heat and mass of the second solution as well.